All right, so for this problem, we want to know how large should n be to guarantee that the Simpson's rule approximation of this integral would be accuracy within 0.0001. So here's the formal statement of the error bound for Simpson's rule. So suppose you have the fourth derivative that's less than or equal to, in absolute value, less than or equal to some k on the interval a to b. So if E sub s is the error involved in this approximation, which we're calling Simpson's rule, then the error in absolute value is less than or equal to this expression right here. We got k, which happens to be the maximum value of the fourth derivative of the given function, and then b minus a, that's the difference in the interval, over to the fifth power over 180 times n to the fourth power. So let's figure out what is our k value, and then everything else will be super easy because we're trying to bound so that the error is within 0.0001. So we want to know k times b minus a to the fifth power over 180 and to the 4. We want that to be less than or equal to 0.00001. So that's what we want to find. So let's go ahead and figure out k. So k was be computed by finding the fourth derivative of this given function. And then we'll try to figure out when will that function have the maximum. And that value, we're going to take it as k. So let's do that. Our function is e to the x squared, as you can see it above. So we know f of x is e to the x squared. So here you're going to be using chain rule to figure out the derivative. First derivative of this function would be e to the x squared times the derivative of x squared. That will be 2x. In other words, this is 2x e to the x squared. So that's the first derivative of f. Let's go ahead and compute the second derivative. So the second derivative of f of x. So here I'm going to compute the derivative of this using product rule and the chain rule. So derivative of 2x, that's 2, keep the second e to the x squared, plus, now differentiate second. So we have 2x, keep that, e to the x squared, the derivative of that is 2x e to the x squared. So if you combine common terms, so you have 2e to the x squared, that's the first term, and then plus 4x squared e to the x squared. So that will be our second derivative. Now let's go ahead and compute the third derivative. So the third derivative of f of x. So let's take a look at this and compute its derivative. So derivative of 2e to the x squared, that's 2 times 2x e to the x squared. Plus, now here we're going to be using product rule and the chain rule. So derivative of 4x squared, that's 8x e to the x squared. Plus, now keep 4x squared, differentiate e to the x squared, that's 2x e to the x squared. All right, so that's for the last piece. So now we combine like terms, clear up things so that we can take the next derivative. So this is 4x e to the x squared. And then we got 8x e to the x squared. And then this last term I can multiply 4 and 2, that's 8x cubed e to the x squared. Now here I can combine common terms. So these are like terms. You can combine them a little bit further before taking the derivative. So I'm going to say this is 8 plus 4, that's 12x e to the x squared. And then plus the rest, that's 8x cubed e to the x squared. So very carefully done. Now we take the derivative of that. So we need the fourth derivative, and then we're going to find the maximum value of that fourth derivative function. So now let's differentiate this first. So using product and chain rule, derivative of 12x, that's 12 e to the x squared, plus the derivative of keep the 12x, differentiate e to the x squared, that's 2x e to the x squared. Plus, now we go to the next term. Now we're going to go ahead and differentiate this one. So derivative of 8x cubed, that's 24x squared e to the x squared. Plus, now keep 8x cubed, differentiate e to the x squared, that's 2x e to the x squared. All right, so that's done, not so bad. Now let's combine some terms. Now if you realize, these are going to be common terms. So you got 12 times 2x squared and then 24x squared. I can combine that. So I'm going to go ahead and rewrite. So this is 12 e to the x squared. That's our first term. Plus 12 times 2, that's 24 x squared. And then we have another 24x squared. That's 48x squared e to the x squared. Plus the last term. So that's just 16 x to the fourth e to the x squared. All right, so we have successfully computed our fourth derivative. So this is the one we need to focus on. All right, now what we want to do, we want to take the absolute value of the fourth derivative, and we want that to be less than or equal to some k. So I'm going to rewrite the fourth derivative this way. So since they all have e to the x squared term in common, so you can kind of factor that out. So our fourth derivative is that expression. So in absolute value, you have e to the x squared times 12 plus 48x squared plus 16x to the fourth in absolute value, less than or equal to some k. Well, we're trying to find the maximum value of this on the interval 0 to 1. So if you look at the problem, our interval, we're integrating this from 0 to 1. So your a is 0 and b is 1. So, well, now we're trying to see, well, when will this function in absolute value will have its maximum on this interval? So you can kind of guess and check the endpoints, and you can also use the closed interval method to find the maximum value of this function by taking its next derivative, which will be the fifth derivative, setting it equal to 0, finding the critical numbers, and then make sure whatever critical numbers lies within this interval, you can test them. So I'll leave a link in the description box for you to check out the closed interval method from previous calculus course if you are not familiar with that. So that's another way to do it. But here I think we can guess and check, and you'll agree that it is sufficient enough to come up with k. So if you plug in 0, well, all of these are going to disappear. E to the 0, that's 1. So the maximum you'll have will be 12. Now, if you plug in a 1 into this function, since they all have even power, that's nice. You'll have 12 plus 48 plus 16. And then e to the 1, that will be e. So you'll have e times 12 plus 48 plus 16. And this would give you 76. So in absolute value, of course, that's positive. So 76e. So we want this to be the k value. That will be the maximum value of this function in this interval. So we kind of analyze it by plugging in values. Now, if you try to plug in numbers in between 0 to 1, it wouldn't give you the maximum. We can test it out with numbers such as 0.5 and so on. So we got the k value, so that is what we're going to set k to be. So let's find the error bound. So we want the error, which is k times b minus a to the fifth power over 180 times n to the fourth. We want that to be less than or equal to 0.00001. So we wanted the accuracy within this decimal place. So let's plug in k. So we're going to plug in k, a, and b, and we're looking for n. How large should n be? So we know we're looking at the interval 0 to 1. So this is your a, this is your b. So k is 76e and b minus a. So 1 minus 0 to the fifth over 180 times n to the fourth, less than or equal to 0.00001. So this will give us 76e over 180, and then I can multiply both sides by n to the fourth and divide by 0.0001. So this is 0.00001 less than or equal to n to the fourth. Now here you do need to use a calculator to figure out this number. So the last thing you would do is to take the fourth root of this number. So if you take the fourth root of this number, 76e over 180 times 0.00001, you'll get your n value, less than or equal to that. So in other words, so after I plug this in my calculator, I get about 18.4 less than or equal to n. In other words, we want n to be greater or equal to 18.4. Now, since the Simpson's rule requires even number of intervals, we're going to go with the next even number after 18.4 because you can't have decimal interval. It wouldn't make sense. So therefore, we're going to choose, as long as n is equals to 20 or greater, you're going to have the approximation within its appropriate accuracy, which is 0.0001 in this problem.